Boris Raychenko, who will tell us about applying local features matching method for automatic Canopus-V. And I think they will continue to work as well once resource B is on orbit.
Good morning, my name is Boris Raychenko and I'm a developer from CTT Group, Russia. Our company is working on scalable solutions in the field of automatization of the most popular image processing operations. Can you hear me? Can everybody hear him well? Okay. Today's report is dedicated to the most popular operation, which is matching method. Here I will show you the sample acquired from Canopus-V, and we'll be talking about applying local features matching method. And it will be a brief report. I will tell you what image matching is all about, where it is used, and what is the particularities of space imagery, which has certain limitations. What is a local features matching method, which came from the computer vision field. And the second part of my report will be about adaptation of the existing functions of computer vision. Here you can see two extracts from Canopus-V and Worldview. Can we say that this is the image from the same location? Yes, we can. And this matching was found by identifying some local particularities. This is a brief illustration of this methodology. It is an frequently used methodology. Everything depends on what we're trying to match. If we're matching it with retrospective or reference data by doing change detection and monitoring, here we can detect some changes, and the precision of matching is, of course, a critical factor in such cases. Matching with reference images is done through georeferencing. This is quite a challenging task, at least for us, for our team, because of a number of factors. First of all, they're related to a number of characteristics of sensors of different satellites and different conditions of imaging. The navigation metadata containing such information about positioning of the satellite and other things contains some errors, and the changes on the in terms of localization can disrupt the algorithm and reduces the precision of angles and other things. And I will show you what I'm talking about. The images from resource decay in Canopus-V. Here we have a dark strip on a dark light background and light strip on a dark background. And here you can see the roofs of houses and ponds and lakes. And it is impossible to see to another image. And green shows the building which is absent on another image. This example is quite a complicated task for a spatial correlation. Still, this is a well-known problem which is successfully resolved in the photogrammetric packages of PhotoMod, among other things. They automatically find the tie points, and the operator will have to filter the erroneously found differences in terms of computer vision. This is one of my favorite subjects. It has other features because the developer or user has the opportunity to find a balance between errors of the first and second class. We used the well-known data of navigation parameters in order to properly filter the erroneous differences. What are the local features? It came to us from computer vision, and it's easier to describe it by their properties. First, it's their sustainability. They show in different conditions, then they're local. They occupy relatively small areas, and the most important property for me is that they're distinguishable from each other. This is called discrimination. The application of local feature matching method has some of the particularities related to those properties. One of them is that we it would be sufficient to work with relatively small areas, especially when we work in the clouded area. It is very helpful. Using the sustainability property, we can find matching even in images taken during different different time and seasons, and the precision will be at the pixel level. Now I'm approaching the second part related to adaptation of the existing algorithms, and here I must make another caveat by saying that most of those algorithms were developed for the processing of regular photos, of consumer photos, and which are characterized by large, well-contrasty planes, clear angles, basically everything which is totally lacking in space imagery. Now, step by step, what do we do? First of all, we receive ortho-transformed, ortho-rectified images as an input, which is done by using navigation data. We also realign histograms of the images. Next two slides show the standard algorithms of detection of key points, and I would like to tell you that this image has some smoothing filters overlaid, and it contains some high-frequency information. You can see how these operations are happening. They're repeated for different scales of images. Here you can see the results of this overlay, and in the finally acquired data, we find local extremes by analyzing the neighboring areas and neighboring scales as well. Here, another difference is that in regular photos, we are looking for points which give us which are the brightest or the most distinguishable. We know from the space images that those bright points will more likely be some flares, and as a result, they will provide wrong, erroneous detection. So we try to minimize these errors. For the Canopus-V, their number could be up to 10,000 of those flares, and all the subsequent work that I'm going to tell you about will be directed at reducing such and filtering away such erroneous flares. After finding those key points, we'll look at their vicinity, and the vicinity is registered as an ingredient of brightness. We can use SIRF, famous algorithm of descriptors, but in general, according to our practice, it's better to use the descriptors, which contain data of about at least 64 elements. We compare the vicinities of those acquired points in order to find the similar points. You shouldn't use metrics on Euclidean distance. It's better to spend your time on building the actual tree so that you can find the second closest neighbor. What is happening after we found the matching vicinities? Unfortunately, it turns out that most of the points, more than 90% of them, were not really discriminate, not special. This is one of the most simple examples. This is again the flared lake. We see that many points are on this lake in another image, but we need to filter them away. The unused algorithms of feedback or cross-check. So it happens in nature, and human beings also, they repeat same structures in some neighboring vicinities, and this cross-check proves to be ineffective. We try to help this algorithm in order to restrict the field of matching by dividing it into fragments. These fragments are divided in such a way so that we will have a guaranteed matching capacity. For that, we take one of the images of a bigger scale to the maximum limit to the error. The algorithm is iterational in terms of how we find new keys and fragments. We reduce the maximum corridor of error by increasing the matching capacity and convergence. I can tell you that this is the most frequently used trick to optimize our computers, and it was a good hook to reduce the mapping framework for cluster calculations. Here we use it for a local feature matching. How do we match these fragments? Within those fragments we have a pair with similar vicinities, for instance, but we know that the multitude of points should be geometrically transferred to another multitude of points. According to our practice, most of such matchings are wrong, and that's why we're not using the method of least smallest squares. We use such algorithms as Ransack. And this is again OpenCV advantage, that we can check consensus in OpenCV by sophisticated geographical transformation, and we know that in this case we need to do it more seriously through a shift. That's why we need this adaptation. Here you can see the found matchings which were geometrically validated within those fragments. After analyzing the multitude of fragments, we have the data about the shifts. Here you can see those shifts as points on the plane. We calculate the systematic component which is encircled there, and that gives us the solution. Others are discarded to get better characteristics. Here you can see the result of matching for the whole multitude of fragments. We used 197 type points with the RMS 10 meters. Here we have about 50% cloudiness, but still we found matching. This method has some restrictions. Unfortunately, it doesn't work well in a location with monotonous texture, with regularly repeating same patterns. Here we need to use other tricks, other methods, unfortunately. According to our practical experience, the matchings can be found in those places where we can see the human activities. These are the data of Columbia University, which show the distribution of human activities. You can see that Himalayas and Siberia are least affected by man activities. Conclusions, very briefly. In full automatic mode, we can process up to 80% of all the imagery. Most of the matchings happen in the area where we can see some insignificant elements of man-made activities. The availability of empiric data allows us to filter away the erroneous matching, and which helps us, which makes it logical to build databases with such reference data. Thank you for your attention. Thank you. Are there any